Actually, some session Wednesday. First speaker is Juba. Sure. Take it away, Francis.
All right, so this is going to describe work based on a series of papers, variously joint with my student, Haile, my longtime collaborator at BGU, Ronnie Stern, his student, Argamon, and recently this new guy, Enrico. And so the problem is grounded in AI, as you might know. Might be able to tell, and I don't assume that you have a lot of familiarity with these problems. So as soon as my clicker works, we'll get started. Did that do it? Oh, God. Okay, let's try that again. All right. Welcome to everybody. Okay, so I guess I'm going to be clicking from here now. Probably. Because the clicker was working. Oh, there you go. Thank you. All right. Good. Right. So, first we'll define the problems. We'll give a basic algorithm, and then we'll get into the maybe meatier questions about, learnability that start to get touch like more complexity aspects of the problem. So, as I said, it's motivated from some AI concerns, right? Where you have some sort of a real world problem. I want trucks to take these packages from these locations to those locations, which gets modeled in some formal description language like PDDL, right, which says, what I can do in this world is I can move the trucks from point A to point B, the truck can pick up packages and so on. That formal description of the, what you can do in the model is passed to an algorithm planner, which, given some start state and some set of desired conditions, like maybe I want the package to be at C, right, gives a sequence of these actions that is supposed to get me from wherever I started to some sort of a state where the package is at C or whatever it was that I wanted. Okay. So we often, or the simplest model for these planning domains, a classic thing is called strips. Which if you took an AI class a long time ago, you probably saw. Okay, so in strips, the domains are given by a set of actions and a set of fluents. Those are relations, but they change value over time. So really, it's that you've got a family of these things indexed by what time step you're on. Both the actions and the fluents are going to be parameterized by a fixed set of typed arguments, right? So the move action has arguments of type truck, location, location. At has type truck and location, and so on. So an action model describes preconditions and effects for the actions, right? So in strips, a precondition is just a conjunction of literals written on those fluents. And then the effects are a set of literals written on the fluents. And the interpretation of this is essentially that in order to take the action, that precondition had to hold at the current step. And after I take the action, the effects will hold at the next step. And so we're going to assume that in the action model, those variables that are appearing are action parameters, as they are here, right? So maybe if move was a action, then at in the preconditions or effects, right, would have its arguments bound to one of these three parameters. Okay. All right. So a problem in strips is given by a set of objects, some sort of initial state, and a goal, right? So grounded fluents are fluents bound to objects from that set. a state in these problems is truth values for those grounded fluents. And the goal is a conjunction written over the grounded fluents. And so a plan is just a sequence of actions now bound to the objects in the domain, right? So grounded actions that is supposed to transform my start state into one that satisfies the goal conjunction. So precisely the way that the problem evolves as you take actions is given by the strips axioms. Okay. So right, a trajectory, you're getting trajectories in these problems, right, are sequences of states. So binding the fluents to all the possible objects and giving truth values to those objects. And the actions that you take in a plan are going to be related to that sequence of states by these strips axioms. So for every triple like this, right, so at time t-1, there's a state, there's an action at time t, giving you a new state at time t. We're guaranteed that the precondition of that action had to be satisfied in that previous state. Each effect literal of that action is satisfied in the post state. And each literal that wasn't one of the effects and was satisfied in the pre-state remains satisfied in the post state. That's called the frame axiom. Okay. So between these, they completely determine which literals are true and which are false in that post state. And so, yeah, solution to a planning problem is a plan, a sequence of grounded actions that takes the start state to something that satisfies the goal. And I'll often refer to those states as pre and post. All right. So in domain-independent planning, you're supposed to be able to write many different real-world planning problems in these formal languages. And the problem that we want to face here is, how do we get these formal descriptions of these world models? So a naive approach to doing this with machine learning would be to just treat it as a supervised learning problem. Okay? So, these actions look like they're just functions mapping pre-states to post-states. So let me just try to treat that as a supervised learning problem, like it's classic pack learning. And the basic problem that happens here is distribution shift, right? So if I'm using a new sequence of actions that I haven't seen previously, I'm going to get to some distribution on states that looks very much unlike whatever I saw previously. In particular, if I'm trying to reach a new goal state that's unlike those that I've seen before, there's no way I can use any kind of a nice pack learning style guarantee to say anything about that distribution that I hadn't seen before. And in particular, the planner can exploit like errors in the model, okay, to try to drive me towards places where, maybe things look better than they should, okay? And the other problem is that I can't learn these preconditions. They're always true in these trajectories that I get. So the always true thing looks like it should be an okay precondition, but it isn't. So, there's been work on learning planning models, okay? But basically, in summary, these prior works, although they'll produce for you some sort of a model, like a formal domain description, they don't really have guarantees about correctness. And it is possible to get incorrect models from them. And then, I guess maybe the elephant in the room is reinforcement learning. Probably everybody's heard of it. It's like you take an action and then somebody tells you how good or bad that action was, and then you want to optimize the sum of those rewards over time, okay? So, in all these problems, right, what happens is you get a sequence of observations. Maybe you acted in the world, or maybe somebody gave you some set of observations of people acting, which is passed to your learning algorithm that's supposed to produce that formal domain description. And now, especially in reinforcement learning, the learner gets to choose to make actions in the world, right? So some trial and error. The acting and learning thing is sort of tightly integrated in reinforcement learning. And also in these other models, whenever you would get an error from executing a plan, then okay, throw that example trajectory into the pool and see what we get next. But as a result, these methods are not safe What does that mean? Well, supposing I want to use these methods to train my robot car, I'd really like real data, because that's going to tell me how the world actually behaves, but it might not be so good, right? And, it says, oh, okay, you didn't like that. Okay, well, maybe I came in at the wrong angle. I don't know, it could take a lot of trials, especially for reinforcement learning, to actually come up with a good policy, okay? And that's risky, okay? So we don't like that so much. So we want to get rid of these exploration actions, okay? And this is actually very similar to a model called offline reinforcement learning, which is sort of a cousin of what we're going to consider here. And again, the principle is that because exploration is unsafe, let's just give trajectories that were collected by some sort of an expert, maybe a human driving the car. And based on that, try to learn what's acceptable and what's not, okay? So there's a slightly more subtle distinction between what we're doing with these planning models and reinforcement learning. Basically, a high level, we'll have higher level problems versus what reinforcement learning looks at, which is very low level. Reinforcement learning optimizes a fixed reward function, whereas we'll get some sort of a reusable model. Reinforcement learning tends to use more data than planning models do, but it's because we're making stronger structural assumptions, whereas in reinforcement learning, you just give it sensor data and press go. Okay. So, all right. So we want to do this learning just from trajectories that somebody collected for us, okay? And we want to be sure that the thing that we get out is correct. That's roughly our notion of safety. So how do we do that? A naive approach might be to try to learn an exact description of what happens in this domain, okay? Just say, I want these functions to be correct everywhere. And that doesn't work because these example trajectories I get would often be impossible. It would not be possible to completely identify that domain model, right? For example, if it just happened that some fluent was always true whenever I took an action in that training set, I have no way of telling if that action would have made that fluent true, right? So I don't know if that's an effect of the action. So if I ever tried to use that action in some state where the fluent was false, then okay, I wouldn't know what would happen. And so then I would just get, for a trivial reason, that the learning problem was impossible. Okay, so what we've got in this problem to work with is that training and testing examples are drawn from the same distribution. And in planning, that's going to mean that it's a distribution over planning problems. Right, so start states and goal states. What happens in between is not necessarily coming from any nice fixed distribution, although I do assume that I'm getting examples of trajectories executing plans, solving problems from D, but I don't assume that there was any kind of a nice function that produced these trajectories. I don't assume that there's some, whatever, simple class of linear functions or whatever that takes a planning problem and gives you a trajectory. But I do assume that future problems that I want to solve are also going to be drawn from this same distribution over problems. So this is the basic setup for the learning problem that I'm going to face. And so, to summarize, I'm given the set of trajectories for problems sampled from that distribution, and I'm not given what the effects and preconditions of the actions are. That's the action model that I want to find. And this is probably the most important slide of the talk. These are the kinds of guarantees that we actually get. Okay. So a safe action model is one that only allows the action to be taken if you can be sure that the precondition of the real action in the real domain is satisfied, and if you can tell precisely what the resulting state of the world will be after executing that action. Okay, so that's the safety guarantee. It just says that the plan will execute and it will execute the way you expect it to. There's a complementary completeness guarantee. This is the part that's approximate and probabilistic. And it says, okay, well, with probability 1 minus delta over the training trajectories, I get an action model that with probability 1 minus epsilon over a draw of a new problem from that distribution, the action model is adequate. It contains a plan that gets me from the start state to a goal state. And so let me give you one more example of a, yeah, sorry, Mike.
When you said the probabilistic guarantee, you said with probability over the trajectory. But I thought you said the trajectories don't come from the distribution.
Sorry, with probability 1 minus epsilon over the problems. Okay, you'll get some sort of set of trajectories, right? The trajectories will be for problems drawn from the distribution, but the trajectories in the example problems could be adversarially given. Other questions? Marco?
Is there any notion of like short plans? Because
Yeah, so we should probably ideally have that here, right? And we can add it. It won't cost you anything.
okay. So it's not hard to extend this to the short plans.
No, right? Yeah, and in fact, we'll also get that. Well, we could also get that the plans, the model that you learn will contain plans that are no longer than the corresponding plans that you get as the examples. I don't promise if you give me really long plans for things that have really short plans that I can find the really short plans. Other questions? Sure.
So just in terms of this safe action part, so in the case that you said where you have, let's say, a particular condition which holds before and after an action of the same condition. So you don't know whether that was, if that always was the case in all the trajectories, right? You said you don't know whether it's precondition or not. But always going to be satisfied.
Right.
So what is the, can you sort of give us a hint as to
The way out of that? Yeah. So the way it's going to work is that the model is going to be conservative. And so in cases where you don't know what the effect is going to be, it will prevent you from taking the action. And then it'll fold that into the precondition. Yeah. And that'll actually just come out very nicely from some very simple learning methods. But before I go there, I wanted to give you one more example that might help motivate this problem to this crowd, which is that the action model is basically a non-deterministic algorithm. So here's an example planning domain, right? I've got fluents that describe a configuration of my Turing machine, right? So I is an index into the tape cells. So I have a predicate for the head being at location I, the symbol at I being sigma for each thing in the alphabet. Cell I is adjacent to cell J, and the machine's in state Q for each, whatever. I have big Q many states. So my actions, I could have one action for each symbol, state, and arity of the relation size, right? So the branching of the factor of the non-deterministic machine, where the pre-condition just checks that I gave you the current location of the head, the correct symbol at that location, right? And I guess also should be the state of the machine, and that J is, as appropriate, the cell to the left or right, okay? And then the effect would be, well, the head moves from I to J, so it's not at I, it's at J. I wrote sigma prime at I, and sigma is no longer what was written at I. Okay. So then the planning problem is, okay, so I have tape cells, right, one to polynomially many. My starting state just encodes X followed by blanks on the tape. The starting state is the start state for the machine, and cell I is before cell I plus 1 for all I. Okay. So I want to get to just a state where the Turing machine accepts. So I've set this up so that a plan exists precisely when the non-deterministic Turing machine accepts X within that space. And you can see the trajectories are just these computation histories for a given branch of the nondeterminism, right? The nondeterminism comes in this choice of which action to apply, right? And the only part that depends on the actual algorithm, apart from, say, the count of the symbols and internal states, is the action model. So learning the action model here really is learning a non-deterministic algorithm, given example executions of the algorithm. So yeah, I mean, also like planning is p-space complete unless you bound the length of the plan, in which case it's only NP complete. And so planners are solving these hard problems, and how they do it is not my business. Okay. But yeah, really what I want is to get some kind of an action model that could hand off to your non-deterministic machine. And it will only accept things that are in the language, and it will accept almost everything that's in the language with respect to that distribution on inputs. Okay. So maybe you feel more motivated, I don't know. All right, let's move onward. Okay, so algorithms for basic strips models. And again, of course, that model is a strips model. Okay, so strips is also expressive enough to do some interesting things. Okay. So yeah, the way we do this is the strips axioms, if you flip them around, give you some kind of conservative learning rules. Okay, so if I know that the preconditions have to be satisfied in the pre-state, means that literals that weren't satisfied in the pre-state couldn't have been preconditions. So I can start with all literals and I can cross off the ones that aren't preconditions, right? Looking over the trajectories. Now I know that the effects have to be satisfied in the post state. So literals that weren't satisfied couldn't have been effects. I'm actually not going to use this rule. The one I'm really going to use is the third one, which I can write as saying, if there's a literal that is satisfied in the post state, but not the pre-state, that had to be an effect, right? So if it switches on, that literal switches on, that had to be an effect of the action. And that's really the one I'm going to use. So like I'll start from all possible precondition literals and just cross them off as I see them violated. And I'll start with no effects and add them as I see things switch on when the action gets taken. So yeah, just as an example, like I start with this trajectory. And for this move AB action, I say, well, okay, what are the things that were true? The truck was at A, the package was at C, maybe that's my precondition. That shouldn't be there. And then another observation, if I see the package someplace else, here the package wasn't at C, so I cross off that literal. Do this for all the actions I see in these trajectories. Okay, right. So thinking of states as sets of literals and also precondition sets of literals, right? I can write the learned precondition that I get just as this intersection over the pre-states. And it's easy to see that the true precondition is a subset of this, right? Because, well, the actual preconditions had to be satisfied in all the pre-states for the actions. And likewise, I'm going to use this estimate, the union of all the things that switched on, as my effect set. And the only things that switch on are effects. So I know that it's a subset of the possible effects. Okay. And so really the only concern here for safety is whether or not, or what happens for the effects that I didn't see. Now here, look, I mean, every effect either is in every pre-state or was missing from it one time, okay? If it was ever missing, wasn't true in the pre-state, I will see it switch on when I take the action. So it gets included as an effect. On the other hand, if the literal was always there in the pre-state, it's going to remain in my conservative precondition. Okay. And because these actions have to be consistent somehow, that is, it can't have both the literal and its negation as an effect, right? That wouldn't make sense. That doesn't, that would give you some sort of incoherent state. Because of that, the frame axiom will guarantee that if this literal was true in the pre-state, it remains true in the post-state. Okay, so then regardless of whether or not that literal was an effect, it's true in the post-state, and the this conservative model will correctly predict that that fluent is present in the post state. Okay, so it's safe in that it's going to correctly get the set of effects for the actions, and the preconditions will always be satisfied. Yeah, Antonina.
One thing that I'm not getting so yet. Another problem. I think that you start that you could only go from something being unsat to sat, not the other way around.
Say that again?
So you're saying starting everything unsat and setting it. Do you also have something for negations? Can something that has been set become unsat?
No, I mean, it goes in one direction, right? So I start with all the literals in the precondition, I just cross them off as I see things that would violate them. And I start with nothing in the effects, and I only add them as I see them switch them.
But not switch.
I don't switch them off, right? Yeah. And again, like once I add them to the effect set, I only do that when it had to have been an effect of the action in this simple model. Other questions? So it's safe, and now we can also prove this sample complexity bound, right? So given this number of trajectories, so it's scaling with 1 over epsilon for the probability of solving new problems, linear in number of actions times number of fluents. That's actually the size of these grounded action models, plus log 1 over delta for the bad probability over the training set. And yeah, it's easy to see that the algorithm executed in time that was linear in both the input and output. And yeah, the sample complexity is also linear in the size of the action model. So that's good. Okay. Yeah, sorry, Mike.
So the phrase permits solving a new problem.
Yeah,
What is the meaning of that?
the meaning of that is that, right, so the action model will specify that, some set of trajectories are allowed, right, or consistent with the Strips axioms. And what I mean is that there should be a trajectory consistent with the axioms that gets from the start state to the goal state in that problem.
Assuming the problem is solved.
Yeah, that's right. And you can have, right, so you could have a distribution that includes unsolvable problems as like no instances from INTM. Safety will guarantee that no trajectory there would ever accept, right? And so yeah, you should probably limit the length of the plans that you search for in that case. What will guarantee is that on the subset of the instances that are solvable, the S instances, right, we get at least a 1 minus epsilon fraction of those.
So you rate that the state action model or ensures that the set of trajectories is a subset of.
Yes, that's correct. Okay. So we've shown safety of this method. Right? So really, all I need to show is this completeness. And informally, we'll say that I'm going to specify this in more formal detail in 30 seconds. But an action model is adequate for plans drawn from the distribution D if with high probability the preconditions allow executing that plan. And we'll show with high probability this conservative action model algorithm is adequate. So precisely for my set of learned preconditions, that action model is epsilon adequate for this distribution over planet problems and trajectories if the probability that the learned preconditions don't hold for some action in the trajectory associated with that problem is at most epsilon. And we'll argue that action models that aren't epsilon adequate can only be consistent with the trajectories with probability it's exponentially small in the size of the training set. And this is pretty simple, right? Because we're just focusing on these preconditions. Okay. If the action model was not epsilon adequate, that means that there's some action where I didn't see it observed in this state where the precondition was violated. Okay, but by definition, right? Therefore, it can only be consistent, if I miss that in all of these M samples, right? And as each one's independent, so the probability that that bad action model, inadequate action model survives after M examples is 1 minus epsilon to the M, and okay, that's the expression. Okay, so that's pretty simple. And now given that, right, we're just doing the usual thing. I'm just counting the number of action models and taking a union bound over them, right? So the probability that the action model is consistent after this many examples is, delta divided by the count of the number of action models. So I can afford to take a union bound over all possible action models. Okay. So therefore, with probability 1 minus delta, only adequate action models survive, and the output of my algorithm in particular must be adequate. Right. So yeah, it's a standard style learning theory argument, and the only difference was in what our bad events were. Okay. So right, that was all grounded, right? So with objects actually just bound in everywhere. And it's important to talk about lifted models because then you can generalize to different size domains, and they're also much more compact, right? Each lifted fluent corresponds to a number of fluents that's polynomial with the exponent given by the arity of the fluent, right? So it's important for us to be able to learn these lifted representations. And we'll do this under some assumptions, okay? So first of all, as I said, I'm going to assume that the preconditions and effects were bound to action parameters. And in particular, I'm going to assume that I get trajectories where the bindings are unique. That is, the same object is not bound to two different parameters of the action. This is the injective binding assumption. And in most cases, this is true just because you get some sort of a trivial no-op effect if you bound the same thing, right? Like in the logistics domain, in the Turing machine domain, the same cell was not adjacent to itself, right? There are things you can do without the injective binding assumption, but it gets a little ugly, so I'm going to skip it for today. You can look at the paper if you want to know, but once you have this injective binding assumption, it's not hard because you can directly read off from the trajectory, right? What should be that parameter, action parameter. Okay. So what we do is we're just applying the same rules, okay, but then converting the grounded literals back to the literals in terms of the action parameters, where we actually record what are the preconditions and effects. So yeah, to be concrete, okay, in this move example, right, if I have move truck AB, then only the literals that are bound to these parameters are relevant, right? So only these black literals. All the other green ones have state C or the package in them. So they're not relevant here. And if I look at what happens on these black literals, right? Maybe initially I had the empty set of effects, and I had these effects on the object X being at state Y or Z. Okay, because those are the two locations in the one object I can talk about. After I see this effect of the move action, right? I see, okay, well, initially, the truck was at A and not B, so I can cross off these literals about, X not being at Y and X being at Z, because I know that I can substitute X for truck and Y for A and Z for B. Right, so I just map them back to these lifted literals, and then I can do the learning as before. Ditto with the effects. Okay, so there's nothing very complicated there. All right, so let's get to some basic learning theory questions. Right, how rich a family of action models can be learned. In particular for preconditions and effects, what can I learn safely and efficiently? We have some work on learning probabilistic effects. I won't talk about it today. And some other things I also won't talk about today about other observation models like partial information. Okay. So for preconditions, the first observation is that I can reduce supervised learning from positive examples for a class to safe action model learning with preconditions from that class. It's relatively straightforward, right? I just have this set of examples where I just start in some state that I want to know the label of, right? And some action gets taken there. And because the model has to learn safe preconditions just from these positive examples, right? Whatever precondition representation it produces for you, right, will only allow, can only allow that action to be taken in cases where the precondition would be satisfied, right? That is, I got the set of positive examples and I get a representation that is only true for positive examples. And so if I'm able to do that, with high probability is appropriate, then for like a 1 minus epsilon fraction of the positive examples, then that was a learner in this positive example only learning model. And that was studied extensively in the early days of learning theory, right? In particular, Natarajan, observed that the optimal safe concept is just the intersection of all consistent concepts. So for example, if I'm trying to learn half spaces, right, the best thing you can do is look at the convex hull of the data. And in particular, right, an early observation was that disjunctions are not learnable because for any, say, input that I haven't seen before, it's going to be consistent with the disjunction that says, oh, not that point, right? So the intersection of not that point for everything I haven't seen before, well, is just the set of points that I have seen before, right? So in this setting, the learner just memorizes and can never generalize. Okay. So how far can we push the preconditions, right, given this knowledge? Well, axis aligned boxes are learnable, right? If I just look at the min and max value of each coordinate, that's definitely the intersection of all the axis aligned boxes. Okay, and you can argue that that generalizes appropriately. Unfortunately, you can't do much more than that, right? So Goldberg observed that even in dimension 2, half spaces are not learnable, right? Because like if my data lies on this circle, okay, that convex hull, right, is just tangent to the circle at each of those points. And so I'm just memorizing points on the circle, right? Anything I haven't seen, like, could be where that half space cuts off. Okay, so again, you just memorize, and it's either impossible to learn or takes an exponential number of examples. Likewise, Kivinen showed that complements and unions of intervals in one dimension are not learnable for basically a similar reason, right? I see these points on the line, and anywhere there's a gap, that could be where that forbidden interval lies. Okay, so again, you don't generalize, you're just memorizing points on the distribution. Okay, so that basically closes like what you can hope to learn, in terms of preconditions. So what about effects? Well, one thing I can say is that even if I allow some error, like in a numeric setting, if I allow some numerical error in predicting the post state, I can reduce approximate interpolation for C to the safe action model learning problem with effects from C, right? Okay, what is approximate interpolation? Well, basically, I should satisfy this condition, right? I want a uniform bound on the infinity norm of the true function and the thing that I learn. And so, naturally, the sample complexity of this problem is given by the VC dimension of this class, right? Indicating when I would violate that uniform interpolation property. Okay. And so, in particular, right, that VC dimension of this class gives me this sample complexity lower bound. And in the case of, say, Boolean functions, this thing is actually just collapsing to the VC dimension of the function class. Now, I mean, so this tells me a lot about like what classes are not learnable, right? Because if they have a high VC dimension or infinite VC dimension, then I can't learn them or can't learn them efficiently. It's still open like exactly what condition gives you safe action model learning in general, simply because as we've seen and we'll see further, right, it depends on the interaction between the preconditions and the effects. But anyway, so what's the most general thing I know how to learn? Well, okay, supposing for a minute that the observations are errorless, then I can learn action models where preconditions are conjunctions of intervals with linear equality constraints, and the effects are affine functions. And the algorithm, well, I mean, I do the obvious thing for the intervals, and separately, I just write a subspace containing all the pre-states as a set of linear constraints. And then I solve for the affine effects on that subspace. And note that the data has full rank on the subspace it spans, right? So I can actually solve for that set of affine effects. Okay, it's safe because on the one hand, for sure, the interval that I learned, well, those were, things that were within whatever bounds are in the preconditions. And subspaces are closed under span, so therefore the true subspace must contain the span of the observed data. Right, so I'd safe preconditions, and then this observation about the data having full rank on its span tells me that, okay, that affine transformation is uniquely determined on that subspace, right, that the pre-states are guaranteed to lie in. So therefore I get safety, right? That affine transformation is just uniquely determined. Okay, so that's a safe action model. And completeness, well, I can bound the VC dimension of the preconditions and effects, right? And so, yeah, so it basically follows that, from these like standard VC dimension bounds that, okay, the for a sufficiently large set of preconditions, anything that was consistent with all those preconditions is going to be, adequate with this probability. Okay, so that's enough to get my completeness guarantee. And I'm skipping some details here, but it's very similar to what we did in the first thing. It's pretty standard. Okay. Let me just very briefly talk about conditional effects. Okay, so back in Boolean domains, previously the actions had preconditions and the effects were literals. A conditional effect is a little richer, right? It's given by a pair. There's some sort of a condition for the effect that's given by a conjunction. And the interpretation is that the literal only becomes satisfied in the post state if the condition was satisfied for the conditional effect, right? If there's some literal in the pre-state that wasn't the effect of some conditional effect with the satisfied condition, it remains the same. Okay, so there's just a switch on each of the effects now. Right. Now, let's look at the complexity of the problem of learning an action model when there are conditional effects. Okay. And it turns out that actually it's a lot harder. So, again, I've got this set of, I got this distribution, right, on problems, actions A influence F, and suppose the conditional effects have size up to K. Okay, some parameter here. And now if I'm getting with probability at least 1 minus delta, a safe action model that's containing solutions to the problems with probability at least 1 minus epsilon, then I needed at least this many examples that is in particular exponential in the, exponential in the size of those conditions for the conditional effects. So, if I don't limit the size of those conditional effects, then this ends up being, exponential in the domain description size. So I can only hope to give you an efficient method if, say, I've restricted this to be some kind of a constant. So probably don't have a lot of time for the proof of this. So let me just skip it. But yeah, it's cute. You can ask me about it if you're interested. Let's just look at the algorithm. Okay, so I'm going to be able to learn with this sample complexity, right? So it's similar to the, essentially optimal. I had for conditions of size k, I had this, a times f times something that's like f to the k. So it has optimal sample complexity for a fixed precondition size. And the other interesting thing to note here is that, okay, it's, I'm allowing the preconditions to be a k plus 1 CNF now, right? So not just a set of literals, I have a set of clauses of width up to k plus 1, but it's returning for me a set of a precondition with clauses of size up to k plus 2, and I drop that limit on the size of the conditions for the conditional effects, right? So this is a kind of an improper learning algorithm for this model, and maybe we can see why that's appropriate. So what we're going to do is we're going to track for each action the clauses that might be preconditions. This is just some generalization of tracking the literals that could have been preconditions. And for each candidate effect literal, the with k clauses that were true whenever the effect occurred and those that were false whenever the effect failed to occur, right? So these are the things that could possibly still be conditions for that effect. Anything else must not be. And the action is safe for all candidate conditional effects if either, okay, so the effect literal was already satisfied in the pre-state and then I don't care whether or not it's a conditional effect, or all the remaining candidate clauses are false, right? In which case I know that it must not be an effect, or all the remaining candidate clauses are true and therefore no matter which one actually was a condition, the effect occurs, right? And if I look at these conditions, this corresponds to a big conjunction. This corresponds to a big KCNF. So I can rewrite this condition as a k plus 2 CNF just by distributing over the, so I have the OR of these three things, and then I just distribute over the big OR in the this CNF here. So I'm going to give you a precondition for the action that's given by that k plus 2 CNF and all the k plus 1 with clauses surviving that could still be the actual preconditions. And the effect literal is going to be given by a conditional effect where the condition is the conjunction of all those remaining possible conditions. So it's safe because, well, for sure, I included all the true precondition clauses, right, just like before. And I know that this CNF ensures that whether or not the effect occurs is determined on anything that's going to pass this condition. Right. So indeed, I'm only going to allow actions that actually execute, and I'm only going to allow them in cases where for every literal I know whether or not it's true in the post state. For the sample complexity, now we're going to just track the state of the data structure. That's keeping track of what clauses could be conditions or not. If the corresponding precondition wasn't 1 minus epsilon adequate, then with probability at least epsilon, the trajectory contained a state in which one of these things was violated. Either some extraneous precondition was falsified, or some but not all of the candidate conditions were false, right? So that CNF for being able to determine the effect of the action, right? Whether or not the conditional effect occurred, right? That thing was violated. And either the effect actually would be observed to occur or would not be observed to occur. And basically, in each case, some clause is deleted, right? Either I get rid of that precondition, or those clauses that were false when the effect would occur, right? Those couldn't have been the conditions for that literal. Or these clauses that were true when the effect didn't occur also couldn't have been preconditions for conditions for that conditional effect, right? So no matter which one happens, a clause gets deleted and the data structure can't be in that state afterwards. Okay, so again, like before, right? With probability, if the data structure gives you an action model that's not epsilon adequate, it only survives with probability at most 1 minus epsilon, and then after m trajectories decreases exponentially. So again, we just count and take a union bound. Okay. So just to wrap up, we were learning a safe planning model by learning a conservative action model, and we get safe, efficient, and approximately complete learning for these relational strips models, the strips models with conditional effects of small size, and these numeric models with affine effects and this intersection of interval and subspace preconditions. We're working on learning more general types of stochastic domains. Also, there was a work on stochastic domains that I didn't talk about at all. We have some work on learning from partial observations, and we are continuing to work on learning in these continuous state spaces, actions with duration, and so on. All right, that's all I have.
Question.
Yeah.
I was wondering, does your algorithm give some guarantee of minimality in a certain sense of what you're learning?
Well, I mean, so Marco had that nice question about the plan length, and it's not hard to see that because, in particular, we're ensuring that the action model allows the trajectory associated with each of the actions with high probability. It's allowing you to find plans that are no longer than whatever appears in those training examples, and whatever there's some adversarial function that maps these problems to examples. We're going to guarantee that we get plans that are no longer than those. Now, otherwise, regarding like the count of the literals in the model or something like this.
Well, is it the most compact representation of the world as you've seen it during learning?
In general, no. Right. I mean, yeah. So, for example, these preconditions may contain extraneous littles. I mean, in fact, look. I mean, I could always delete all the preconditions, but that wouldn't be safe. Whether or not the safest or the most compact thing that is safe, I guess okay. I mean, again, assuming that it's of this form, I guess the answer should be yes, because right, I need the intersection of all the consistent action models, right, and yeah, so basically, right, the only things that got ruled out were violated literals. Okay, so therefore that safe model, right, can only delete the literals that were violated. Right, if it deletes anything else, it's not safe. So then, yeah, I mean, I need all the literals in that action model that I return in order to guarantee safety. So in that sense, yeah. And I guess ditto for the effects in that basic strips model, right? I needed to have all those effects in order to guarantee safety, right? Yeah. So yeah, I mean, but it's such a simple representation, right? You can start to see that I get things that are not minimal, like if you were to try to learn half spaces, right? Because then the convex hull of the data, in general can have exponentially many faces, even if there was just that one half space that would have been correct. Other questions?
Thank you again.